Yep, come on everyone. Can you look at this? This is the solar system. Meaning, if you look at the far view, no, that is the orbits. This is a game. Actually, it's a simulation called Universe Sandbox. You can do all kind of nonsense in this. Now, see, there is an Earth going. You can see that orbits. You can actually mess up the mass of the Earth also. Now, see, if the mass is there, let's put it on pause, and let's take the mass of the Earth and make it more. Oh. Now see what happens. If I start the simulation now, the Earth and the Earth have become binary stars. You messed up the whole thing. Let me show you this in another way. So let's put it on pause. You can actually add more stars also. So we can add more suns. Here I'm putting one sun here. Equidistant. Now if you start the simulation, now there are two suns, right? It should be a binary star. Why is the sun not moving? I forgot to rebalance it a bit. Now see. Can you see the two suns, how they're rotating? The two suns have become a binary star. Yeah, remaining planets are gone for a toss. You can do even something more crazy. You can add more suns. We have created a supernova. Everything is just blasting. You can see these planets going in different orbits. Yeah, it's a nice simulation actually. You need to just work on this. Anyways, so that is how you can create multiple stars in multiple systems. The best thing about the software, right? It actually simulates literally everything. You just mess up one thing, how the other planets get affected and all. The name of that thing is Universe Sandbox. It is fun when you put 10 suns and everything kills each other. Yeah, but let's see. Anyways, getting back to this. So this was the last thing that we did. Next thing, Kepler's laws. The first law. So all planets revolve around the sun in elliptical orbits with sun at one of the foci. And I hope everyone knows the properties of the thing, an ellipse. The 2A is your major axis, 2B is your minor axis. If you take this focus F1, if you take this focus F2, if you choose any random point here, F1P plus F2P is 2A. Area of the ellipse is pi AB. This is your first law. Now you need to understand this Kepler, right, actually is not a scientist. This guy, where he used to stay, there used to be an observatory which had the data of almost, all the stars, orbits, and everything for around 130 years ka data. So this guy just took up all the data and he started fitting in. He's more like a data scientist, you can say. He had a lot of data, and from there he figured out all these laws. So first law. Second one. The second law states that the area vector is equal in equal intervals of time. Meaning, if you take the sun here, let's say from here to here, it took you time t. And in the same time, you would have gone from C to D also. So the second law says this area OAB is equal to area OCD. And we can prove this. So from the sun, if you take a vector here, r bar, in small time dt, this will travel a distance of v dt. What you get is a thin rectangle. So area of a thin triangle. Area of a triangle is half a cross b. So here it is half r cross b dt. Multiply and divide by mass. This would be mr cross v by m and dt. This becomes rate of change of area is angular momentum by 2m. This is called as aerial velocity. Quite a useful formula. And we can see here, torque about the sun is zero. Therefore, angular momentum about the sun is constant. Therefore, dA by dt is constant. That means you cover equal areas in equal window of time. So second law is nothing but another form of law of conservation of angular momentum. This was asked in CET. Kepler's second law is another form of what? Energy, momentum, linear momentum, mass, something of that sort. This is quite an important result. Have a look at this. Clear? Next one. Third law. The square of the time period is proportional to cube of the semi-major axis. So we have t square is proportional to a cube. Now this thing we already written it. So if you have different ellipses, as long as the semi-major axis is same, it doesn't matter whatever is the time period. This is 3, this is 2, and this is 1. So for the blue one, this is the focus, the center. So the red one will be somewhere here. The green one will be somewhere here. All of them have same major axis. So the time period is independent of minor axis. And we proved for circle, the time period is 2 pi by root gm, a power 3 by 2. A is the radius. So this should be same for everything. So must be same for ellipse also. Because you said this is the same time period. And energy the last time only we wrote it. Minus g m small m by 2. This is for elliptical orbit. There, quite a useful results. Have a look at this. If you look at this thing is a pretty good simulation here. You can look at the speed here, see. The sun is here, as it goes away, the speed decreases. Then as it comes close toward the sun, the speed increases. So basically this is kind of going in an ellipse. Wish I could stretch this more, I couldn't stretch it. So basically it's going in an ellipse.
You can adjust the centricity.
Oh hey, kahan pe? Oh, I tried that before. This thing is not moving actually.
Oh, okay.
Yeah. Nothing is working here. I'll send you this link. You guys can play with this. I think I sent you this thing already before once. Anyway, this is the second law, see. So he divided this thing. Why then there's a weird sound, right? Better. There, you can see here it's divided into 4 parts. For each time interval, the time interval is same for each one. You could increase this to, let's say, 6 parts. So you divided the entire ellipse into 6 parts. The time taken to cross at each point is same. There is giving the years and the date, see. It takes around 0.31 years. The third law is simply the time period. That's normal anyway. Look at this thing. Here you can create a binary star. This was fun. So here, make say mass, follow center of mass. We have 2-body system. And go. There, that's your binary star. See how they're going. Since both are equal mass, they're going in proper circles. But let's say I mess up the masses like this. Follow the center of mass and then play. You can see there. The thing is going in a smaller circle, this thing is going in a bigger circle. This was the binary star. Suppose if you have 3 bodies, I think this would be difficult to adjust them, I guess. Follow center of mass. Shit. They destroyed each other. Okay. They just killed each other. Shit. Let's put third one here and this thing, can I just move it somewhere here? I think I can put them on a triangle. I have to adjust them properly. I don't think this will work. They're killing each other. Shit. Anyway, so this thing I'll send you. This is a simulation from that Colorado. They tried their best. Limited options, but yeah, it's pretty good. You can keep up to 4 planets there. I couldn't adjust them properly. Let's see a question. So we have an ellipse and this thing is going in an orbit. So S is the sun, this is A, this is B, C, and D. Compare time taken. So time taken from DAB and DBCD. Basically, equal to, greater than, less than. Second, what is work done by gravity? The sun is here. So this guy is attracting the planet. Earth is going like this. Earth or some planet. Work done by gravity from, when you go from A to B, what is work done by gravity? B to C, C to D, and D to A. I just want you to tell me whether it is positive, negative, or zero. Chalo, get this thing. It's an easy one. Right, Haryan. Nice, Astuga. You're saying it in reverse. Check it out. Let's see. The first thing, even though it looks like there's symmetry, they're not. The question says the area swept by the radius vector, the area has to be measured from the sun. So when you say S, this is D, and this is B, and this is C, we are talking about this area. And when you're going from DAB, we are talking about this area. You can clearly see the area SBCD is greater than area of SDAB. Therefore, since area is more, time also will be more. So time taken to go from BCD is greater than time taken to go from DAB. You can even actually calculate the values if you have more data. Yeah, speed is more, but you need to understand that radius is also small. So this is the center. This is the focus. This value will be B and this will be AE. So you can find the area of the triangle and the area of this thing. So area of SDCB would be pi AB by 2 plus half into base into height AE into B into 2. That would be pi A by 2 plus ABE. That is the area of SDACB. SDAB would be same thing, but pi AB by 2 minus AB into E. Hope I'm writing right. There. So I need eccentricity on the minor axis. I could even find you don't need to be axis. You can even find the ratio if you know eccentricity. We will cancel out. What about the second part? You're going from A to B, B to C, C to A, D to A. Straightforward. There's no need to check out the values. Just ask yourself this. Work done by all forces is change in kinetic energy. So when you're going in an ellipse, the closer you are, the faster you're going. So at this point, the speed is maximum. You are the closest. Here, the speed is minimum. Here, the speed is something in the intermediate stage. So V dash is less than V max, but greater than V minimum. So work done by all forces is change in kinetic energy. So if your speed is decreasing, work done is negative. The work done from A to B is negative. Work done from B to C is also negative. Work done from C to D is increasing again, it's positive. Work done from D to A is also positive. If they ask you work done from B to D, it would have been 0. B to D would have been 0. Clear? This was easy. So always check out from the speeds, that will be easiest. The closer you are, the faster you go. Sure. This is an easy one, meaning mostly a bits level question. Even at a mains level, they could ask you something simpler. Clear? Next one. Great. Let's see something good. So we have a planet here. You projected here with a speed of V0 from point A. So this guy goes like this and comes and lands on the equator at point B. Mass of the planet is m and r. So you're launching a particle with a speed root over gm by r. Basically, it's an orbital speed at an angle. You're not projecting it tangentially. If you had projected tangentially, it would have gone in a circle. So here the point A is the pole. So you're launching a particle from pole. Angle is not mentioned. And it goes and lands on the equator. This much we know. It's V naught is launched from A and lands at B. Find the time taken. Now, be careful. This is not a parabola. This is not a parabola. Gravity is not constant. And if you remember the trajectories, there are only two closed paths possible, an ellipse and a circle. And this is definitely not a circle. This is an ellipse. Itna to bata hai. Let's see how to do this thing. It's a pretty good one. This is a proper advanced question. They could put this as a paragraph. I can ask you more, but I think if you got this idea, you'll get everything. I hope the question is clear. Think. Take 2-3 minutes. Try to figure out few parts. Anything. Just give it a try. I'll be back in a minute. Any ideas? First thing you need to figure out, it's an ellipse. That I told you. Can you find the major axis of this ellipse? You can find the major axis of an ellipse. How? There is one formula which gives you the major axis of an ellipse. That is marked in green color here. If you can find out on this page. Means if you can somehow find the total energy of the satellite, you will get the major axis from there. And you can find the total energy of the satellite because initially velocity is given, initially potential energy is given. Then what? Yeah, that is right, Rehan. Then what? Next. Major axis, somehow you got it.
Time period formula.
Come again.
मेरा type होना चाहिए.
करो टाइम पीरियड कैसे यूज करोगे? इट्स नॉट अ फुल एलिप्स. Let's see.
2 minutes, sir. Almost done.
Yeah, it has been more than 3 minutes since 2 minutes. We want the time period of the ellipse, not the time taken for you to solve the problem. That would have been interesting question. Let's see the ellipse part, the major axis. Do that. In the time I'll just find the major axis. So you're launching here with V0. So this would be an elliptical path.
So, but how do you know it's an elliptical path?
What do you think it should be then?
You need to prove it somehow, no? Like some locus or
Prove it,
something.
na? Then Arjun. Tell me now, how do you think we should prove it? You had a chance for 3 minutes to prove it. What did you do?
I was trying using the normal acceleration ka function like and integrating that. But then you're getting
that is bullshit actually. What will you do with that? That is bullshit actually. Velocity is this way, acceleration is this way. How will you do that?
Yeah, I realized that later.
How will you prove it is an ellipse? First thing, if you observe, the velocity, right, is between the escape velocity, less than escape velocity. Means you can't get out of the orbit. Right? You can't get out from the orbit, you're stuck. And second thing, when you project, the center has to be the focus. This is the Kepler's first law, isn't it? So Kepler's first law says everything is in elliptical orbits. And where the center of the Earth will be one of the foci. The major hint in this thing is this trajectories which I gave you, if you remember. If you're having velocity less than escape velocity, right? Yeah. First of all, these two are gone. Because for these two to occur, you need a velocity more than escape velocity or equal to escape velocity. If you had gone with V orbit, in this thing you would have got a circle. The only two trajectories left are this first case, isn't it? That is how we figure it out. Because see, there's nothing else. There's no other option there. But if you're trying to prove it mathematically, you'll be stuck. You won't be able to prove. So the particle goes in an ellipse, right, with the center of the planet as the focus. That is the second data point. I don't know whether you figured it or not. The center of the planet as focus, because that came from the first law of Kepler's first law. There he talked about sun and planets, but you can apply the same thing for anything. And what is the total energy here? The total energy is potential energy minus Gmm by R plus half mv0 square. This is minus Gmm by 2R, and but we know for the total energy of an elliptical orbit, minus Gmm by 2A. So we got A is equal to R. So therefore, we know this is a part of an ellipse, and this is your focus, and that's your major axis is A. That means if I just try to draw this ellipse, this is what we are looking at. This was the focus, and this angle is 90 degrees. And that is R, and that is R. So then that means this is also R. This is also R. Isn't this the minor axis then? Isn't it? Because in an ellipse, the sum should be equal to 2 times A. If you look at this distance, this is also R, and this is also R. That means for the ellipse, now, this is exactly an half ellipse. So this is point A, and this is point B. What do you guys think?
So I sent something तो देख लो सही है कि नहीं.
देखते. Monica, there is no center of ellipse. The planet is there. The gravity is acting towards the sun, isn't it? If the gravity is acting towards the sun, shouldn't the center of the sun should be the ellipse? So here also same thing, right? The gravity is acting towards the center of the planet. So shouldn't that be the focus? There is nothing here in the center to attract the planet, isn't it? That way. The sun should be at one of the foci. So here, basically, instead of sun, we have the planet. And instead of the earth, we have the particle. The gravitation is always towards the center of this thing. So that should be the focus. Everyone is clear with this thing? This ellipse ka part? So from here, I can find the major semi-major axis also. If that is R and R, how much is this? This thing is completely R root 2. There, you got everything. हो गया ना? You got the area now. So indirectly, you're asking the question, find the time taken by the projectile to sweep this radius vector ka area. We are trying to find this area and this area. So this length will be R by root 2. This also will be R by root 2 because this is R. So this green shaded area is pi AB. A is R and B is R by root 2. This red shaded area would be
pi AB or pi AB by 2.
pi AB by 2, na? Pi R square 2 root 2. And this red shaded area would be half into base would be R root 2 and height would be R by root 2. That would be R square by 2. So the total area swept by this vector. So this is the total area we're talking about. Is pi R square by 2 root 2 plus R square by 2. And we saw from the aerial velocity for the total area pi AB, we are getting the time period T. So for this area, what is the time period? unitary method. That would be t r square by 2 pi by root 2 plus 1 by, what is pi ab? Pi is r and b is r by root 2. R square cancels off. We end up with there, something like this. And what is the time period t? Time period t, so we know 2 pi root over gm a power 3 by 2. So the whole question is about finding the area. Once you got there, you can finish it off. How did you get AB as the minor axis? In an ellipse, whenever you take 2 points, just now we proved that sum should be how much? 2a. So now you're saying this distance is r, this is also r. So in an ellipse, is there any other point which is equidistant from the focus and exactly equal to a and a distance? That should be the center part, isn't it? When you look at this thing, in this thing, this is the focus. This is a part of an ellipse. This is r and this is r. And you're saying r is equal to semi-major axis. So shouldn't that be the minor axis line?
Yes, sir.
Check it out. Ishan did the same.
Yeah, sir, I did the same, but end में I just put b is equal to root 2r.
वो थोड़ा ध्यान रख लेना.
Hmm.
That thing is full thing is r by root 2. So minor axis b would be r by root 2. So main thing is figuring out that this line is the minor axis. That was a catch in the question. And if you don't know the total energy, you couldn't solve. You can get the major. You won't get the major axis. That's what makes this question really good. Like Arjun said, the first thing is figuring out it is an ellipse. Now, if you exactly want to prove mathematically, you can't prove. But this much you should know in gravitation. We had only what? Ellipse, circle, hyperbola, parabola. These are the only orbits that are possible. They will always form conic sections. You can't have parabola and hyperbola because velocity is less than escape velocity. Can't be a circle. Because if it was a circle, the velocity would have been tangential. Then the only possibility left is ellipse. So that would be the first argument. Then you will say total energy of an ellipse is minus gm by 2a. And I can find the total energy by potential plus kinetic. From there, you get the major axis. Once you got the major axis, that should have given you a hint. This distance is also r. This distance is also r. And these 2 points are on the ellipse, equidistant from the focus. The only possibility that would be a minor axis. I hope that is clear. You could have said like this also. Why can't it be this? These two can't be r and r, na? That can't be the major axis. You guys are experts in ellipse, so you know that. There, once you got the area, game's over. Clear? Good one. Had a lot of things. Since time is a linear function, we can use that unitary method. Or you can say aerial velocity, I know. So let's see one more. Now, this question you can't solve normally with gravitation or anything. You have to go with the Kepler's law. Without that, you can't solve. Next one. So let's say assume Earth is going in a elliptical orbit. Sorry, in a circular orbit. It's almost a circular orbit, but yeah, it's slightly ellipse. So let's assume it is proper circle. Now, for some reason, someone stopped the Earth from revolving around the sun. If the Earth is stopped and released, when it is going in a circle, you suddenly catch it, make the velocity 0, and then leave it. Now, what will happen? Due to the gravitational force, the Earth falls into the sun. This is another good standard question, actually. Find the time taken for the Earth to fall into the sun. Meaning, see, I'll tell you what is happening. So we have the sun. This guy is happily going in a circle. It's going with some speed v. So at any point, if you see the centrifugal force, G/m by r squared is gravitational force, and the centrifugal force balance out. So you can say that is the reason it is going in a circle. Now what you did, you just stopped the Earth ka velocity, you made it suddenly 0. So if velocity is 0, there is no one to stop you. Only the gravity is pulling you in, G/m by r square, you'll just go straight and crash into the sun. Normally for one revolution, it takes 365 days. So the question is, how much time will this Earth go and crash into the sun? I hope the question is clear. Try.
It will depend at where it is when it is stopped.
Sub circle I got. Why will it matter? You mean this points on a circle are different?
Oh, I took it ellipse.
Circle, na? How do we do this? Two 29.93. It's not precision.
So wait. One second.
Till final major axis. Yeah, right. Rehan, that would be right. Then that was the logic then. You can't keep an RM. दिया ना time period 365 days. नहीं ईशान, I think you got it. इतना क्या accuracy up to 2 decimals. You are using calci क्या? Leave it in roots ना God. करना normal exam में कहाँ पे calci लेके जाओगे?
It's hard to type in the roots now, so I just use calci.
ठीक है, but answer is wrong.
Okay.
So that looks right. Shan, it's a one-way journey.
Yeah, sir. हाँ उसका half होगा. Sorry.
Once Earth goes
Is it
into this
correct
and it
now?
won't come back, it is bye-bye.
Is it correct now? Half. If we have that value.
Let's see. क्या करना है? Listen, everyone. The idea is pretty good here. So initially, when you have velocity v, you are going in this circle. Now suddenly don't make it zero. Let's try to assume, let's see what happens if you decrease the speed slowly. If you decrease the speed little, then instead of a circle, you'll start going in an ellipse. You're getting it? Simple reasoning also. What is the potential energy of an orbit? Minus gmm by 2a. If you decrease the speed, energy decreases. So the value of a will start becoming smaller. Now, if you decrease the velocity even more, let's call this thing v1, then you will go in an ellipse. You can see the ellipse is becoming more eccentric, something like that. It's becoming more thinner and more flattish. As v tends to 0, you will get a case where this is a case where v tends to 0. As v gets pretty close to this, it almost becomes a straight line. As the speed decreases, right, the ellipse will actually start shrinking. It goes in an ellipse with a decreasing major axis. You're getting it? So if you see here, v is greater than v1 is greater than v2. So as v tends to 0, you'll observe we get an ellipse. Where b tends to 0, the minor axis will start tending to 0. Basically, you're making it a line. So in that extreme case, this is what happened to this. This has literally become a line. It's a very thin ellipse. So here, this major axis is r. And for the blue one, initial orbit, the major axis is 2r. So that means you can assume when v almost tends to 0, it goes in an ellipse whose major axis is only half of the previous one. Then using Kepler's third law, we know t square is proportional to a cube, the semi-major axis. So t1 square by t2 square. So this guy would be r cube by the major axis become half of it, so r by 2 whole cube. So this thing turns out to be t2 square would be t1 square by 8. So t2 would be t1 by 2 root 2. T1 is nothing but 365 days. But remember, this is for the full trip. This is the full time period of that ellipse. But the question is only one way. So for the Earth to go into Sun, it will be half of this. The time taken would be T2 by 2. So this would be 365 by 4 root 2 days. I think if you calculate this approximately, yeah, you can round off 65 days. Or it is 65.52349378, something like that, like someone typed here. So 65 days. That means you have barely 2 months left. So if Earth actually stops, first of all, we will die immediately, I guess. But even if we survived, you won't live for 65 days. Within 5 to 6 days, Earth's temperature will exceed 100. We will get fried. So anyway, it is not a good thing. Please have a look at this thing. There, the satellites was especially the good part in this. With that, we're done with gravitation. So most of the problems we saw in electrostatics were quite similar, except that you saw that especially the satellites and all that, that is where it was a little different from electrostatics. We did only 15 problems, but all 15 were pretty good. Especially if you remember the starting with tunnels only, we played with 6 different cases here. That was a good one. Even in tunnels, there was one new concept I taught you, center of gravity calculation. Give. So center of gravity here, this one is there, and we had this space elevator. This was fine. This was fine. This was also a decent question, proper mains level question. Satellites main, yeah, a little bit of a theory. This one again, life cycle of a star. That could be a good explanation. This was also a good one. Stable orbit for NK value. That was a pretty good one. This is also a good one. Meaning, I just did all the good ones only in this satellites ka part. This is another good one. Rocket thrusting and all this thing. And with that, we're done with this thing. There is a movie, meaning exact aisa movie nahi hai, Ishan, but there is a movie where the sun is getting exhausted. The sun is going to blow up supernova. So these people try to take away the sun from the solar system to some other galaxy. And they create something called Earth engines, and they do. It's a Chinese movie, but it's a proper Chinese movie, and they build something called Earth engines. They build something like 30,000-40,000 of them. They put thrusters and they pull the thing away from the Earth. So interesting movie. So while traveling on the way, the Jupiter is there. The Jupiter starts attracting the Earth towards it. That was the meaning. That was the villain in the movie, Jupiter. So how will Earth escape from the Jupiter gravity and go away? That was the story there. And they do pretty crazy stuff. So as they're going now, the Jupiter was there. It is pulling out Earth's atmosphere's oxygen. So the hero there in a orbit, he decides like, yeah, we should do something interesting to blow away. So he comes to a conclusion: Jupiter is made of a lot of hydrogen gas, and Earth's oxygen is going. So if I ignite this, there will be a blast, and Earth will get pushed away. So they blow up Jupiter in order for the Earth to escape from the Earth's gravity. It's something, I know, it's practically it is like nonsenseful physics, but it looks fun to watch. It's a proper Chinese movie. I saw it with subtitles, so yeah. हाँ, उसका नाम भी है Wandering Earth. It left a very big impact on me. Blowing up Jupiter to get away from the thing. So in that movie, Jupiter was the villain. Anyways, so that was one. So next thing we'll be starting off with waves. So waves is another interesting chapter, but technically, if you ask me, as long as you remember the results and the standard stuff in this waves is quite an easy chapter and pretty scoring. The main thing, you should just have a basic idea of what is happening and all. And hope you all have seen the results. Results were out. If you see, the guy who got that 795 rank, his score was 236. I think that's around 66% score.
So, but they give like 30 marks bonus or something else. Yeah.
Advance mein?
Yeah, like at least I don't know. There were a lot of questions.
No, wrong only. So advance mein every wrong bol rahe Arjun.
Like I don't know.
इतना कुछ नहीं है रे. People will say उसमें गए. Those who had problems, they had did this thing. But ठीक है ना, 30 marks bonus. Everyone must have got it. So I think there's another guy who got 191. कुछ तो था. His rank was 2,700. 700ish. So 176 gave a rank of 4,4545, something like this. 175 ka rank was 4,800 something. There's almost 200 ranks ka gap for 1 mark. Huh? Then one girl student got 156. She got 8,700 something. 155 mein rank was 9,135. So this is what will happen if you don't cross that 65%, 60% border mark, right? For every 1 mark, you'll start losing 400, 500 ranks. There's a big cluster, Once you go below that 180, there's a lot of people there. For each mark, you start losing huge number of ranks. So, but on the higher zone, right, if you cross 60%, 65%, for 1 mark, you still lose maybe like 10 or 20 ranks. But as you come to the lower level, it just blasts off. I think 137 mein rank crossed 13,700. So for girls, right, 8,700 rank, she's getting IIT Hyderabad mein electrical. IIT Bombay mechanical is on the border. Matlab 8,000 mein last year, IIT Bombay civil. So this boy who got 4,500 and the girl who got 8,700, both are getting same options. That is the power of 20% reservation. So girls should definitely use this advantage to full. And कुछ ज़्यादा नहीं है, it is not like a big difference. 20 marks का difference था. So you can think like that. So girls, you have an advantage of the 20 marks almost. But seriously, because the better rank you get, the better options you have. Because in the top 1,000, the number of girls are very less. Socho na, the girl who got 180, 200 rank, she's getting IIT Bombay Computer Science. Because in top 200, barely you will find like what, 8 to 9 girls. Now IIT Bombay mein computer science ka seats are I think 60 seats. In that 20% is for girls. So 12 seats are there for girls only. Now for boys, you need to be in top 50 to get into IIT Computer Science. So do put effort. You still have a year time. Yeah, mother, exactly 6 months time is there. But I'm telling you seriously, relentlessly start preparing. Don't leave a single day. Don't even think about anything other than this. And it is worth it. Trust me, it is worth it. Yesterday night only we had a session with your seniors, like Kaunsa College, Kya Lena hai, brought a counselor. He was guiding them, what college and all. First 1 hour it went well. Second 1 hour people became idiots, I guess. खड़गपुर में फूड मिलेगा, खड़गपुर के बाहर डोमिनोज पिज्जा एक ही है. I said, bloody Domino's pizza, so what that has to do with IIT Kharagpur? People had all weird discussions. I said, ठीक है. I think all got tired, I guess, and they wanted to have some fun. So that was there. Will there be AC in the hostels? IIT, somewhere, यार, कुछ तो discussion था. IIT Goa? No, IIT Jodhpur, I guess. Something. Last year there was no water talk. Semester got over in 2.5 months, so people got more holidays. There were all weird discussions. But anyway, they finished their exams now, so they can do all that shit. And yesterday was my last class for them, actually. That was the last session we had for them. So that was one. And we are planning a get together, like last year. Mostly it will be this year on July 7th. So please make sure to attend. You'll be getting an official invitation. We'll be posting it in 1 or 2 days. Your seniors also will be coming. So let's see. So let's start it off. So waves. So what is this exactly? So first thing, let's start off with something more fundamental. Disturbance. So what is a disturbance? So disturbance is simply the change in property with respect to the surroundings. Think of like this. In the class, if someone is talking, why does a teacher shout and say, why are you disturbing the class? That is because everyone is quiet, only that guy is shouting. So here the property that is changing is intensity of sound. What if everyone is shouting in the class and this, then it is fine, right? And teacher will shout everyone. That's a different thing. But the property is same everywhere. So disturbance is simply the change in property at a point with respect to the surroundings. Example, if you take a bulb flickering in a room, so here the change in property is the intensity of light. So technically that's what it means. When you say disturbance, it means that some property is changing. Now that property can be anything. So here the property that changes is intensity of light. Now when you say property, this could be anything. The property can be displacement, electric field, magnetic field, density, pressure. Property can be displacement, pressure. Electric and magnetic fields. So the property changing is electric and magnetic fields. We call it as a light, right? Density, so on. You can just keep on creating any kind of properties you want. So if I take a more technical example, so just consider we have a wave like this and consider this point A here. Now, as this wave pulse is going from left to right, you will observe the point A goes up slightly, the point A reaches the peak value, the point A starts coming down, and the point A comes back again. So if you look at the total motion of A, as the pulse is traveling, this point A is simply going up and down. So here the disturbance or the property that changes is the displacement of point A. So a pulse on a string, the property that changes is the displacement of the particles. Have a look at this. So this is the first thing you should know. That disturbance is what exactly? Next thing. The propagation of disturbance is called a wave. Now, if this disturbance propagates, let's say the student in the first bench shouts, then he stops, and the second bench person shouts, then he stops, and the third person shouts, and he stops and fourth shouts. Now we'll think, yeah, the disturbance is propagating. You can see this thing in a queue also, isn't it? When you're standing in a queue, the guy from the back pushes, the disturbance propagates. So the disturbance here is the persons are getting displaced from their main positions. So here the people are not moving. They'll come back to the same position. What moved is a disturbance. The propagation of disturbance is called a wave. So that would be a more technical definition of a wave. You can also define wave like this. So in a wave, energy and momentum are transferred without any transfer of material. Now waves can be classified into mechanical and non-mechanical depending on the medium. Mechanical waves and non-mechanical waves. So in mechanical waves, they require medium to propagate. Like waves on a string, sound waves. These things do not require medium to propagate. Example, electromagnetic waves. We have a separate chapter for the ZM waves. We will deal with those things later on. But in our thing, we will be only sticking to mechanical waves. There. Now, this is one way of classifying based on the material, but there is a more better way of classifying depending on motion of the particles. Turning the page. Any doubts so far? Clear? Just a theory. Don't worry too much about it. You'll get the PDF anyways. Next. So you can classify waves based on motion of the particles. So the first one is transverse waves. So in transverse waves, non-mechanical waves other than EM waves, generally no ray moleka. That is the only thing that we have so far. The particles or the property, like I said, the property thing is electromagnetic and all. We will discuss that in EM waves. They oscillate perpendicular to the wave propagation. That means if a wave is going to left to right, the particles oscillate up and down like this. The best example, waves on a string. So this point which is there, A, so you can clearly see here, this point A was here, then the point A went up. Let me draw one more. And finally gone. So if you look at the particle A, the wave is going front and back. The wave is going forward, but the particle A goes only up and down. This is what I was saying. The disturbance is going forward, but the particles are oscillating up and down. This you'll observe in a beach also. When you go to a beach and if you throw something, the particles are simply going up and down. Or ever went to a water park, the wave pool? When you're sitting in a wave pool, when the wave comes, you're simply going up and down. You're not going front and back. So what you're doing is the waves in a thing is a transverse wave. One of the best example, right, is your water waves or even a tsunami. Tsunami is a transverse wave. You know what makes tsunami dangerous? Wavelength. So any wave, right, what happens? This is what happens with any wave. Normally, if you see the continental shelf, now this is how generally a beach looks like. This is called a continental shelf. Now, if this is pretty shallow, it's a good beach. For example, if you go to Goa, beaches like this, you can just walk for 1 kilometer and still you don't sink. But if you go to a place like Kerala beaches, right, they're like this, pretty sharp and they're pretty bad, meaning you will just sink. So for a place to be a good beach, you should have a very shallow continental shelf. Now, what happens when a wave is coming? Now, in the ocean, there is no problem. Now, as the wave enters here, what will happen? The moment it hits the continental shelf, the front part of the wave is slowing down. The back part of the wave is still coming faster. So this wave will climb this. You're getting? The wave in the front is slowing down. The wave at the back is still coming faster. So the wave which is horizontal will start becoming like this. It starts going up. It starts piling up on itself. And once it reaches a certain height, that is almost 70 to 80% of the wavelength, then it collapses. That is what you see in the beach, the water going and hitting and coming in this. Now, generally in a beach, right, the wavelength is around 2 to 3 meters long. So the wave height is also around 1 to 2 meters. A tsunami has around 10 kilometers ka wavelength. Huge. Meaning, if you see why tsunami comes, it is because of the continental shelves. They are huge waves. And what is the best place to be, when there is a tsunami? In the ocean. Because imagine you're on a boat here and the tsunami is coming. Remember just now what I said? The particles simply go up and down. So the tsunami is so big, you'll simply climb the tsunami. You don't even know you're on top of a tsunami. The tsunami is going below you. Only while maybe climbing it and while coming down, you'll notice there is some kind of turbulence and all, but you're actually pretty safe in the deep ocean. Huh? The word is that. Deep ocean. The most dangerous place is the continental shelf. Wave is coming at full speed and hits you pretty hard. And after that, once it hits the coastline, the height of the wave almost reaches 100 to 200 feet. 100 to 200 feet is, we are talking around 20 floor building, 20-30 floor ka building with a speed of almost 300 kilometers per hour. It just sweeps everything into the thing. It enters almost 3 to 4 kilometers, it will just push through. Then, and before tsunami comes, normally the water starts receding. That's your first sign. And you will see a lot of fish there. So don't get greedy and go get them. You'll go get the fish, the sea will come and take you. So tsunami is this thing. So during 2004, I guess, there was a big tsunami that happened in Malaysia. Philippines, Malaysia, that area. I was in school that time, 11th standard, I guess. The tsunami was pretty big. Normally after an earthquake, right, generally you get a tsunami alert. But during 2004, no one really cared much about it. There was no systems and all. That thing devastated entire Malaysia. Philippines, Malaysia, all the islands got devastated. Then, that thing started traveling towards India. It reached from almost Singapore to India and reached in 3.5, 4 hours. That's the speed of a flight. And the sad part, no one in India no one knew it was coming. The first thing that got hit was Andaman Islands. There, the Indian Navy reported was something is coming big. That is when the first signal went from Andaman Islands to Chennai. Then the Chennai port authorities got alerted. They started sending signal, get out from the beaches, come outside and all. But they had only 1 hour time. But by that time, the tsunami was also carrying the same speed. It hit the coast. Literally, city. There were villages which got wiped out. This thing personally I knew also. Meaning, we heard about the stories when I was in IIT Madras. There was a village called Nagapatnam. It was there today. Next day morning, it was not there. No one left. Swept away. The entire village is gone. Out of existence. There is nothing there to see. There is a village there. Literally, entire Tamil Nadu coast got battered. After that, people decided we should have a early warning signal. See, when a tsunami comes, you don't have a choice. You have to run. But you need time to run away. So this is the system that we use normally. So when there is an ocean, right, we introduce buoys. These buoys, kabhi dekha, beach mein, they look like this cone kind of things. Ever seen them? They're just floating in the beach like a buoys. So this is a concept. So we are going to install some buoys every, let's say, 500 meters. Now, when a tsunami comes, what will happen? See, the tsunami will come. When it goes, this buoy is connected to a GPS. This will go up. So in your system, the computer, the light will glow that this thing went up. You say, okay, one se kya hoga? Kuch nahi hoga, maybe an error. But after some time, when the tsunami enters here, this also will go up. Now the lights will start glowing, one after another. Now, when the tsunami has reached here, this guy will come down again. So this will light up and this will go off. Did you observe what happened? We found the length of the tsunami. Isn't it? These things are coming down, these things are down, and all the central lights are up means what? That is the length of the tsunami. Second, I can find the speed traveling from here to here. I can estimate the speed of the tsunami. Then I can send a warning signal. Tsunami is coming in next 90 minutes. Please evacuate. This much you can do. So this entire warning system is based on transverse wave concept. So just knowing the property of a transverse wave, you can create a system, to detect tsunamis. Again, I just gave you a very rough idea, but that is how the basis is. Take a break, come back to 7 to we'll continue from here. Sure. Cams on, everyone. So this is transverse wave. The second thing, longitudinal wave. So in longitudinal wave, the particles so in the direction of the wave propagation. That means if a wave is going this way, the particles are oscillating this way. Example, sound. Now, if there is no sound in the region, this is how the molecules would look. I'm just representing the molecules with a line. Molecules are almost equally spaced. Now, the moment you apply sound, you will observe some points get compressed, some points get expanded, some points get compressed, some points get expanded. This is what you studied in school as rarefaction and compression. Best example is, when you're standing in a queue and someone gives a push from the back. That's actually a longitudinal wave. So here the particles are oscillating in the direction of the wave. Now, have a look at this.
Hi guys,
This
today I
is
just want to show
slinky.
you a demonstration of transverse and longitudinal waves using a slinky. Now,
You'll get this in Amazon for 300
transverse
rupees.
waves, the direction of energy, which is what the wave is going to travel through, is going to be
Now see,
moving
when you push it up and
perpendicular
down,
to the direction of energy transfer. So, let me give this a go.
now that's a transverse wave. You can see this thing is going up and down, but the wave is going forward. I'll show you another more clarity one.
So you can
That's a
see the
transverse wave.
pulses or the waves are moving from the left to the right. So the energy is moving from the left to the right, but the actual slinky itself is moving perpendicular to the direction. Moves in the same direction.
Now, if you
as
look at the
energy
longitudinal
transfer.
wave,
So the energy is also a longitudinal wave.
it looks like this. See? So you're pushing it left and right. Can you see the difference? How it is getting compressed and expanding? So if the wave is going in the direction of this thing, it's a longitudinal wave. So on a slinky, you can generate both the types of waves, a transverse and a longitudinal wave. Look at this. There. This is a transverse wave. You kept a slinky on one side and you're pushing it. You can clearly see the wave, how it is. The wave is going forward, but these things are oscillating perpendicular to this thing. There, that's in a slow motion. If you observe any one point on that slinky, you will clearly observe it's just going perpendicular to that motion there. There. Amplitude, crust, wavelength, we will talk about that. This is a longitudinal wave. Say. So this is a transverse wave. Now look at this thing. Can you see that pulse, how it is traveling? The pulse, the compression is going front and back. Now this is a longitudinal wave. The particles are moving in the direction of the wave. I hope everyone's clear with this thing. You get a slinky, you can play, it does a lot of interesting things. That is one. There, you do have a simulation also in this Colorado thing. So there, this thing I can go up and down there. So I can keep giving pulses and it will start oscillating. Here I can have different things. I can have a damping. If I have a lots of damping, we did this in SHM, if you remember, high damping means if I give a pulse, see, it died down everything. I had to give big pulse, it dies down. It doesn't come back much. But if you have low damping, if I give a pulse, everything comes back. So there's no damping, there's no energy loss. But now see, if I just increase the damping, the wave dies down. Right. So, and I can have an oscillation there. I can increase the frequency. If I increase the frequency, it will start oscillating faster and faster. We'll have more closer. This is a low frequency. I can have high amplitude, low amplitude. I can have high damping. If I have high damping, you'll observe as the wave goes to the right, did you see it is dying out? Wave right side, it is not even reaching only to the right. The wave is slightly reaching. So if you decrease the damping coefficient, it does reach till the end, but you lose a lot of energy. You can have all cases also, loose end, no end. Yeah, you have a lot of cases. We will see this later on. So as we see, this is one thing I'll send you this link. You can have it, for reference. It helps because the problem with the waves ka chapter, try observe now. Mathematically, you'll understand everything, but you'll feel like what nonsense is happening. You won't believe it. That's the problem. So once you get that feel, right, this thing is actually happening. Yeah, no damping means no loss of energy. Damping is like friction, right? Viscosity. So that visualization thing is quite important in waves. That is one thing that I noticed. If you really don't feel it like, this is actually going to happen, you're never going to believe it. Problems also you will do with half-heartedly, like you will do it. It doesn't give a feel. So you can go and play with the simulations there. Helps. Next thing. So whenever you talk about waves, there are three properties. So if you know these three quantities about a wave, you can you know everything about the wave. So there are three quantities. Which are required to study a wave. So if you give me these three quantities, I know everything about the wave. The first one is frequency. The second one is wave speed. The third one is amplitude. There. So if you know these three quantities about a wave, you have all the information. So let's see what each one means. The first thing is frequency. We use the symbol F. So frequency is simply number of oscillations or number of waves per second. Simple definition. Now a frequency will depend on the source and independent of the medium. So think about it. If you're shouting 10 times per second, why will the medium affect how many times you're shouting? No matter whoever is there, they'll hear only 10 times the sound. And this is one of the reasons whenever a light travels from one medium to another medium, frequency remains constant, wavelength changes. That's the reason a red color light will still look red even if you're underwater. So color depends on frequency, not on wavelength. If the frequency changes, the red light should look like a different color when you're underwater. So frequency does not depend on the medium, it depends only on this thing. So generally, the most common device we use to get this frequency is a tuning fork. So the tuning fork, it generates constant frequency. That's it. That is the only property about it. It generates constant frequency. Let me show you how it looks. I'm sure you must have seen this. There. This is how a tuning fork would look. So these things here, which are there, these are called prongs. So when you have this tuning fork here, if you call this point as A and call this point as B, and when they oscillate, understand how they oscillate. They will oscillate like this. They'll come together, they'll go away together. They'll oscillate like this. Getting it? They don't oscillate like this. They come and go away together like this. That means if you look at the equations for them, this is point B and this is point A. So when B goes to the right, A goes to the right. So the equation of A will be, it's basically an SHM. X is equal to A sine omega t plus pi, phase difference. Whereas the point B will go with A sine omega t plus 0. So the two prongs have a phase difference of pi. Isn't it? This is going from the mean position towards right. This is going from the mean position to the left. A and B are out of phase by pi. That means they're going to generate waves on both the sides of different phase difference. We're going to see that later on. Correct? It's a prongs oscillate in SHM out of phase. So if they're coming together also, they would oscillate like this. They will come inside or they'll go outside. And this thing, the frequency depends on the, if you increase the temperature, what will happen? If you increase the temperature, the prongs will become longer. If the prongs are longer, it's more difficult to oscillate. So frequency decreases if you increase the temperature. So if you take a tuning fork and increase the temperature, tuning fork changes. There are other ways also to change the frequency by adding mass and all. We will see that later on. But there, a theoretical question. If you increase the temperature, what happens to the tuning fork of frequency? It decreases. This is how it would look.
Oh!
These are the slow-mo guys.
I was filming that. Sounds like it, definitely. So I've heard that tuning fork.
That is the 1600s tuning fork.
So I have some choice. Really awesome. I've been over exaggerating.
That's it. They're going to hit it and put it in water. Can you see how the prongs are oscillating? You can clearly see the surface tension on the surface. That is oscillating 1600 times per second. It looks like that. We can't figure out it's going that fast. Can you see how the water is sticking to the prongs? That is the surface tension of meniscus thing. It rises with this. There, you can clearly see the water, how it is rising. And now see, you will clearly see the surface tension. Like, water just doesn't come out. It drags it like as if it's like something like sticky layer there. And yeah, this is the best part. When that thing falls on the water, see how it bounces. It's like a layer. Look at the small drop, how it jumps.
Luckily for our
This is
YouTube
also good.
channel, oh, that's all I could be. It was actually option D.
This guy does something more weird. He's keeping it in the mouth.
It was correct. It did look awesome, and
That will hurt pretty badly. Pretty badly. मतलब तो सोचो ना, it is oscillating 1600 times per second. You keep it on your teeth. That means you're oscillating your teeth at 1600 times per second. The inside the root canal or whatever, right, will get literally irritated. So you want to harass someone, it's a pretty good torturing technique. Works. So there, that's your tuning fork. That's how it looks. Now, in tuning fork, right, there are two ways to use this to create waves. Case one, let's say you take a tuning fork like this and you tie the string like this. Now, at this point, when it oscillates, see what happens. Now, this thing is almost like going in SHM. This position is your mean position. And this is your time, t0. And the frequency of this is f. So when the time goes to t by 4, that is 1/4 of the oscillation. Then t is equal to t by 2. Then t is equal to 3t by 4 and t is equal to t. We will see the 4 parts. So this prongs would have looked like this. This point A would go forward. That means this string, right, will become like this. You get an half loop. And when this guy again, basically you're at extreme now here. When it again comes back to the mean position, so you pull the string up, so you will get another half loop. Again, when you go to the left extreme, again, I'm not drawing exactly up to scale. And when you come back to the mean position, you have completed 2 loops. That means if you're going to keep a tuning fork vertically and if you connect a string, every time it oscillates, it generates double the number of waves. You're getting this? So here, f is the frequency of the tuning fork. Generally, people don't use this case. So in one oscillation, we get 2 pulses. Therefore, the wave frequency is 2f. So be careful, just because you use a tuning fork f doesn't mean you always get f. This is one case. The second one, case 2, you keep the tuning fork horizontal like this. This is the case we use most of the time. If nothing is mentioned, we'll take case 2. This is T0, this is frequency, this is the string. At T is equal to T by 4, your tuning fork will go up. So the string is like this. So you only get 1/4 of the loop. Then at T is equal to T by 2, you come back to the mean position. So you have completed an half loop. So you'll get an half loop now. This is the difference between the previous one and this. And when you go at T is equal to 3T by 4, this is like this. At T is equal to T, you come back to the same position. You have completed a loop. So for one oscillation, we get 1 pulse. So if you keep the tuning fork horizontally, the frequency of the wave will be frequency of the wave is equal to tuning fork. In one oscillation, we get one wave. Therefore, wave frequency is f. If nothing is mentioned, we take this case. If someone says a tuning fork f is used to produce a wave, he's talking about the horizontal case. Think about God, when it goes to the extreme position, isn't it an half loop? When the point goes to the extreme position, this is the loop. Isn't this an half? We're talking about a symmetrical sine wave, no? So when you do a 1/4 revolution, isn't the point at the highest point here? That's a quarter loop, isn't it? So keep this in mind. Don't get confused if nothing is mentioned. Mostly if they ask, it will be a theoretical question, or they specifically use the word. The tuning fork is placed vertically and the string is connected. If nothing is mentioned, then assume case 2. Because generally, right, why you want to confuse yourself by making 2f frequency? So if you're taking a tuning fork of frequency 400, it is understood you wanted a wave of 400. If you wanted 800, then choose an 800. Why you want to do stunts? So simple. So this is one thing about wave frequency. This is how you can generate waves using this. So this is the first property, frequency. Second one. All clear with this thing? Case 1, case 2? Turn in the page. Next thing is wave speed. Now wave speed is completely different from particle speed. So what is this wave speed? The speed at which the wave propagates. This is independent of the source, but depends on the medium. Think about it. If you're shouting, you're getting it. Why will the speed of sound change? Because you are running and doing all dances. It depends only on the medium. If you're shouting, if you are sending a sound wave in a solid, it travels faster. In liquids, it travels faster. In air, it travels a little slower. So it is independent of the source, meaning whether you shout or I shout, the speed of sound is same. Independent of source and depends on the medium. Means if you're going to throw a stone into a water, the pulse which you get and the travels doesn't depend on how fast you throw the stone. What matters is the amplitude will change, but wave speed won't travel. Meaning, just to give a more crude example, think of like this. Just think of these molecules, right, are like balls here. They're pretty close to each other, touching like this, almost touching each other. So if a ball comes with 1 meter per second and hits it, E is equal to 1, what will happen? This will hit, this will move, this will move, this will move, this will move. Finally, this will go off, right? Let's say this length is 10 meters, and let's say this ball moves after 0.1 second. So what is the wave speed? 10 by 0.1, which is 100 meters per second. Meaning this energy and disturbance travel through these balls at a rate of 100 meters per second. Suppose if this ball was traveling at 10 meters per second, you will observe after hitting the first ball, this ball will still move after 0.1 second only. You getting the difference? The particle speed is 10 meters per second. Individually, each ball is trying to move 10 meters per second. But that energy and the disturbance propagated through the balls at a rate of 100 meters per second. Or same thing, when you're standing in a queue, think about it. When you push the guy in front of you, that person is moving, then he comes back, then this person moves, then he comes back. The disturbance is propagating at a different speed, whereas the people are moving at a different speed. I hope you're getting the difference. So particle speed and wave speed are completely two different concepts. So when you take this, if you look at here, this is your wave speed, the speed at which the disturbance is traveling. Whereas if you look at this point A, this point is v particle speed, and you can clearly see both are perpendicular actually in a transverse wave. So on a string, velocity of particle or velocity of A is up and down. Whereas the wave speed here, if you try to actually calculate, let's say this is the peak value here, and this is the peak value here, and this is the length L. And let's say the time taken is t. Wave speed is something else. Wave speed here would be the length traveled by time, and the direction here is I cap. Whereas this guy would be j cap. So be careful, wave speed and particle speed are not at all same. They have a relation, but they're not same. Wave speed is the speed at which the disturbance propagates. Think of like this. Let's say you all are sitting in a classroom, and imagine I pass on the assignments, and I say take one and send the remaining back. Now you tell me, when you take the sheet, how fast do you send the sheet, and how fast are the assignments actually going? When the sheet is in your hand, isn't the speed different? You're getting it? The sheet has a different speed in your hand at different points of time. But if you look at the speed at which the sheets are being passed on, maybe the other person is getting a sheet after 1 second, 1 second, 1 second, 1 second, 1 second. The sheets are being passed at a rate of 1 second, 1 meter per second. But whereas in reality, each sheet, the speed is different. I hope you're getting what is particle speed and wave speed. So have that understanding. Both are completely different. Don't get confused. This is your second property. The third one. Amplitude. This is the same definition as SHM. Max displacement from the mean position. This depends on the source and the medium. We saw in that video which I showed you, when there's a damping, right, the amplitude became very small. It does depend on the medium. So their frequency doesn't depend on the medium, wave speed depends on the medium, amplitude depends on both. So let's say if you have an oscillator like this, you tied a string here, and this guy is oscillating up and down like this. Let's say y is equal to a sine omega t. So you will observe, so when this thing goes up, the wave also will look like this. So the amplitude of this wave here will depend on the amplitude of the source. Whatever height you take there, you will get the same thing here. Clear? So these are the three properties. So if you know these three properties, you can find all the information you need for the wave, how much energy it is carrying, what speed, what time, everything. There. So that is all the theoretical part of the wave. Now let's get into a mathematical formula, like how to represent a wave in a mathematical form. So we studied what is a waveguide definition. We studied the properties of a, what do you call it, the types of waves, and then we studied the three important properties that are in a wave. Let's put a mathematical formulation. All clear with this so far? Next thing. Now, wave equation. Now, remember how we defined a wave? A wave is nothing but the propagation of disturbance. So we will define y, which is a property. Now, y could be y coordinate, y could be anything. It could be pressure, could be displacement, electric field, magnetic field, blah, 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 etc. So if you plot y versus x graph, so this is the graph of your disturbance as function of time t. What do you mean by this exactly? For example, let's say this is intensity of sound, okay? For example, that means the person who is standing here, let's say x is equal to -1, he will hear like this, something like this. The same person, when he stands at the origin, he will hear more intensity. The person here will hear again slow. When you go from left to right, it is like goes up and comes down. So we are plotting this on a graph like this. So this could be an intensity. It could be anything. It could be brightness. It could be electric field. It could be displacement, anything. So this is a property as a function of x. And now you're saying this disturbance is propagating forward with a wave speed, v wave. So this disturbance is moving continuously. So at this topmost point, this value is f of 0. And this curve is y is equal to f of x. So after some time, this disturbance from here has gone ahead. Like this, the disturbance has gone ahead. Meaning now this point, after some time, this point ka coordinate became vt comma 0. But still we know this point ka value should be still f of 0. So we are just using, shifting of origin. So if you want this point to be f of 0, what should we do? So the equation becomes f is equal to y is equal to f of x minus vt. Is that making sense? Think about it. See, when you put x is equal to vt, I should get f of 0. So what will be the new equation? F of x minus vt, shifting of origin. So basically you're shifting vt comma 0 as a new origin, isn't it? And when you shift the origin, what you do? You subtract the coordinates, if you remember. So the equation becomes x minus vt. So this is the equation of this thing. F of x minus vt. If the wave was traveling to the left side, it would be x plus vt. This is a x minus vt or vt minus x. Same thing. It doesn't matter. This is called a right traveling wave. If the wave travels to the right, you'll get x minus vt or x plus vt. We will talk in more detail what is exactly f of x minus vt. Till now, we are used to learning things in f of x, f of t, but this is a function which depends on two variables. The wave depends on both x and time. Same thing, see, if the wave had been traveling to the left, just think of like, displacements also. So after some time, the pulse would have got shifted from here to here. So the peak value must have come somewhere here. This coordinate will be minus vt comma 0. So to get the peak value f of 0, the function should have been f of x plus vt. So if someone writes an equation f of x plus vt, it's a left traveling wave. So let me write the final thing. So the general wave equation is y is equal to a function of, remember that, function of x plus minus vt. Plus indicates left traveling wave. So that one sign will tell you which way it is traveling. Minus indicates right traveling. So what is this y exactly? The y is a property. Now again, what property? It could be density, it could be electric field, it can be displacement. It's a property which changes with position and time. That is the meaning of that f of x plus or minus vt. It's a property which is changing with both position and time. So these kind of waves are called progressive waves. The wave is traveling only in one direction. Now, for example, let me tell you what do you mean by depending on two variables. Huh? For example, right now, all of you are there. I'm studying the position of your right hand for all of you. You getting? So y, what I'm getting, y is the position of your right hand for all of you. Now look at the problem here. When I say right hand of all of you, what is x? X will tell you which person I'm looking at. So if I say like, Aryan, so x ka value is fixed. Now look at Aryan ka hand. So at different times, I'm looking at Aryan ka hand, isn't it? So every one of you, there are multiple right hands here, and every right hand is moving at differently in different times. So how do I study all of you at the same time? You get the point? So when you say f of x plus or minus vt, means you're studying the displacement of the hand, where x is the position of the person and t is the time at which you're observing the hand. Is that making sense? Now, in this, if I make, again, it is difficult for us to observe both at the same time. So let's see, we will do one study at a time. It is difficult to study with x and t at the same time. This is not the first time. We always had this problem. For example, in ideal gas equation PV is equal to nRT, how many variables are there? Pressure, volume, temperature, moles. How did we always study? We always kept two things constant, isn't it? Number of moles, temperature constant, we studied PV is equal to constant, Boyle's law. We kept volume constant, we studied P proportional to T. So when you had more than two variables, you always kept one constant and studied the remaining two. Because we are unable to comprehend these things in 3D. When x and t changes at same time. So this is what is happening. So if you look at our waves here, every particle is going differently. This guy is going up, this guy is coming down, this guy is going up, down, down. So we need to somewhere focus on the study. We can't see everything. So in this equation, let's see one at a time constant. So in the equation, if we keep time constant, what am I looking at?
A photo of a wave, kind of.
Photograph means, look at this again. Try to understand the meaning of this. I'm looking at all of your right hands at a given time. Means what am I saying? I took a photograph of all of you and your hands are like this, stuck. So now I can see all of your hands at the same time. You're getting it? So when you say I'm keeping the time constant, you took the photograph of a wave. I'm just looking at all of you at a given time. Means if I say I'm looking at your right hands at time 7 o'clock, at 7 o'clock I took a photograph and I'm looking at your right hands. We are looking at all points at same time. That is a photograph. So if someone tells you, so this is important, if someone tells you this is the y-x graph of a wave, means he's talking about a photograph. Meaning this is actually the position of the particles. The y-x graph of a wave is a photograph. I'm using for a string, okay? What if x is constant?
It will be like the video of a one particle.
Basically, I'm looking at just one of you for all the times. If you keep x is constant, meaning I'm fixing the position. So I decided to look at one of you, your right hand, throughout from 0 to infinity. So you can do only one of them. I can look at all of you. It is like focusing on something, right? Happens na? When you're going on a road or something, you're just having a focus on everything. The moment you try to look at the front vehicle, you can't see what is happening on the side. Either you can have a full view or you can have a focus view. But the problem with the full view, you won't get full data. You can get data at a point, at a single time. So when you say x is constant, we are looking at a single point for all times. So be careful. If you're drawing a YT graph, you're actually drawing the oscillations of one point. We are looking at one point at all times. So a YT graph is kind of like SHM only. You're just looking at one particle. So be careful. Even though the graphs would look same, they are completely, their meaning is different. A YX graph and YT graph will mean a quite different thing. I hope this is clear. Clear? Going ahead. So how do you decide how does an equation look like? So there are three conditions any equation has to satisfy for it to be a wave. An equation has to satisfy three conditions to represent a wave. One, we proved it. It should be in the form of y is equal to f of ax plus or minus bt. X or plus or minus bt. So the coefficients are fine. You can have anything. And here v wave, if you just take out that a common, you'll get x plus or minus bt ka form. So v wave here is coefficient of time by coefficient of a. Meaning if you just take out that a common, you get x plus or minus b by 80. So there now it looks like fx is plus or minus vt. Coefficient of position b by a. The second one, if you take y is equal to fx minus vt, there are two variables here, so I have to do partial differentiation. Dou y by dou x would be f of f dash x minus vt. If I differentiate this again, dou square y by dou x square, this would be f double dash x minus vt. Same thing, if I do partial differentiation with time, remember it's a chain rule, the x minus vt ka differentiate karna hai, so that minus v will come out, and you have f dash x minus vt dou square y by dou t square, double differential. This would be v square, again this is v wave square, f double dash x minus vt. Now something interesting you'll observe here. If I use the first equation there, you'll end up with quite a useful result, most neglected one. Dou y by dt is minus v wave dou y by dou x. Dou y by dou t is what? The velocity of the particle. Because y is the displacement of the particle. This is the relation between a particle speed and wave speed. Dou y by dou x is nothing but slope. This is the relation between a particle speed and a wave speed. This is more important. Then the second equation, dou square y by dou t square, that would be v wave square is dou square y by dou x square. That comes from equating these two second differentials. That is fine. That means like So what this means is logically now, what is the whole meaning of this? The whole meaning of this is the function should be continuous and differentiable. That's what the second thing is trying to tell you. Meaning, if you ask in layman terms, what is all this double differentiation and everything mean? This means the function is continuous and differentiable for first differential and second differential. And it makes sense logically. So, if the function is not continuous, means what? Try to understand the meaning physically. Means there is a wave, suddenly it vanishes, and suddenly wave comes from nowhere. You can't have a wave which is broken in the middle, isn't it? So if the velocity is not continuous function, means acceleration is not defined. If position is not continuous, means velocity is not defined. So when you're saying you're talking about a wave is a physical quantity. It actually exists in nature. So you can't have a wave vanishing and coming from somewhere. So the second point, the whole meaning is the wave has to be continuous and differentiable. You can't have breaks in a wave. But that is the meaning of the whole thing. But in that, the quite an important one is this result, the one in the red box. This is also a good one, a basic question. Third, the function should be finite and bounded for all x. When you say finite, automatically it is bounded. For all values of x and t. Meaning you put any value of time and any value of position, the function should never go to infinity. Again, kind of makes sense. Why? If the function goes to infinity, means what? The amplitude can go to infinity, means energy is infinity. Not possible. So you can't have an infinite energy system in real life. So these are bounded functions. There, if anything that satisfies these three conditions is a wave. Have a look at the points. That thing in the red box is quite important, quite a useful result. Particle speed and wave speed correlation. All clear with this? Let me give you a question. So I'll give you some functions. You have to tell me which one is a wave, which one is not a wave. And if it is not a wave, which condition didn't satisfy? So the first question. Y is equal to x minus vt whole square. Y is equal to sine 3x minus 2t. Y is equal to cos square x plus t. Y is equal to sine x square minus v square t square. Y is equal to 2 by 3x minus t whole square. Y is equal to 3 by 2 plus 2x minus 3t whole square. Y is equal to x by 3 plus 2x plus t whole square. Y is equal to e power x plus pt. Y is equal to e power x minus 2t whole square. Y is equal to ln x plus vt. Yeah, these things should do, I guess. What do you guys think? Which ones are wave functions? If it is not a wave, which condition is not satisfying? Just give it a try. Take a minute, finish it off. Just give it a try. I'll be back in a minute. Let's see. Let's go in an order. The first one. It's not a wave. Why? It's not a bounded function. If x tends to infinity, y will tend to infinity. I said you can keep any value of x and t and still it should be finite. You keep any value, shouldn't go to finite. So this is gone. It doesn't satisfy third condition. Second is fine. Sine function is bounded. Third is also fine. Cos square is bounded. This is interesting. This is gone. Most people will say, sir, but it is looking like x plus vt, x minus vt. It should be either x plus vt or x minus vt. Matlab socho aisa. When you say it is a function of x plus vt, the meaning of this, you know what? If I replace x plus vt with z, I should not see any x and t anywhere. Isn't it? When you say I'm replacing x plus vt is one complete term. So if you replace x plus vt with z, right, there should be no x and t anywhere. But this function, sine x plus vt and x minus vt, if you put this as z, this is still stuck. I hope you're getting it. Sine AB, there is no formula there. It's not sine A plus B. Getting it? So this is gone. This doesn't satisfy the first condition only. First is gone, so second is also gone. Getting it? So it should be either x plus vt or x minus vt. You can't have both. Third is also gone. It is unbounded function, goes to infinity. If 3x is equal to t, it blows off to infinity. This is right. Because, this value is what? 0, right? 3/2. That is still finite function. This is gone. Doesn't satisfy the first condition. There's an x sitting here alone. This is also gone. Unbounded function. It goes to infinity. This is again right. E power minus x square, na? This value is always less than 1. This is gone. Ln 0 is undefined. Please check. So don't think like every time wave function will look like sine x plus minus vt. You can have any weird wave functions also. But we will be limiting the study to only sines and cosine functions. So if you see, even this was a wave. Even this was a wave. But we'll not be studying such functions in our study. Clear with this question, everyone? Anyone that is not convinced with anything one particular, especially the fourth is a slight confusing thing because people think x plus vt, x minus vt, both are there. That is a problem. Both are there. Meaning, for example, look at this here. If I put 2x plus t, 2x minus 3t is equal to z, this will be 3 plus 2 by z square. See, there is no x and t anywhere. So the entire x plus vt should be one term. Clear with this? So there. So that's the last one for the day. So next class, when we catch up, we will do more problems on wave equation. So the theory part was there. There's a bit of a theory we did today. So we will do more wave equations. Then we'll see sine and cos waves. We will study them separately. And then we'll start off with wave speed also in the next class. So we'll go in that order. First, we'll finish off waves on a string. Then we will go for sound waves. We'll go one after another. It's a decent chapter. It's easy actually, but you should know your basic standard models and the formulas and stuff. Okay, so with that, we'll wrap up for the day. So remember that there's a test online till tomorrow night, 11 o'clock. So make sure to give. Don't forget that. And it's a 40 questions ka test. So there is a 90-minute time I gave. So do keep that.